Welcome back. In today's video, we're diving into the architecture behind one of the most widely used financial tools in the digital economy, the digital wallet. From PayPal and Venmo to Apple Pay and Alipay, digital wallets have transformed how we store, transfer, and manage money online. They're not just a convenience feature. They're the infrastructure powering billions of dollars in transactions every day, in real time. So, what exactly does it take to design a digital wallet system? Well, a lot more than a simple send money button. Behind the scenes, you need to ensure strong consistency, fault tolerance, auditability, and performance, often across a distributed, high throughput environment where downtime and errors can have serious financial implications. In this video, we'll break down the essential building blocks of a scalable, production grade digital wallet system. We'll discuss how to manage wallet balances securely and in real time, support peer to peer transfers, and potentially foreign exchange, ensure reliable and atomic balance updates across users, and choose between distributed transaction models like two-phase commit, try, confirm, cancel, and the saga pattern. We'll also take a deep dive into event sourcing, a powerful architectural pattern that allows us to trace every change, recover from crashes, and replay entire transaction histories with precision. By the end of this session, you'll understand not only the core components of a digital wallet, but also the trade-offs and engineering decisions needed to ensure safety, speed, and scalability in financial systems. Let's get started by defining the problem and exploring the core requirements. The problem is to design a digital wallet service like what PayPal offers. Here are some good requirement questions to ask. Are there any features we need to support other than balance transfer? How many transactions per second? How about the availability requirement? How about foreign exchange? Let's walk through the high-level design of our digital wallet system, which supports real-time money transfers between user accounts with strong consistency and resilience. We begin with a simple API layer that exposes a key operation, a post endpoint that allows clients to initiate a balance transfer from one user to another. To ensure fast access and minimal latency for balance lookups, we use Redis as an in-memory key value store where each user balance pair is stored. Redis is sharded to handle high concurrency and large-scale user traffic efficiently. The wallet service orchestrates the core logic. It processes incoming transfer commands, coordinating balance deductions and credits across user accounts. Now, this is where things get tricky. In distributed systems, you must ensure atomicity across multiple data stores, meaning both the debit and credit should succeed or fail together. We explore three major distributed transaction models to solve this. Two-phase commit, 2PC. Here, the wallet service acts as the coordinator. In phase 1, it asks all involved databases to prepare the transaction. If everyone replies yes, we go to phase 2, where it asks all to commit. If any say no, the transaction is aborted. While 2PC ensures strong consistency, it's prone to blocking in case of node failures. Try, confirm, cancel, TCC. This model splits the transaction into three parts: try, confirm, and cancel. First, resources, like reserved funds, are tentatively allocated in the try phase. If all participants respond positively, confirm commits the transaction. If any participant fails, cancel reverses the reserved resources. A phase status table helps keep track of each operation's status to support eventual consistency. Saga pattern. Here, each step of the transaction is independent and local. Operations are executed in sequence. If one fails, compensating transactions are triggered in reverse order to undo the prior steps. Sagas are highly scalable and fault-tolerant but require thoughtful design for compensation logic. Finally, we incorporate event sourcing to improve auditability and state recovery. A command represents the user's intent, e.g., transfer $100. An event is the outcome, e.g., $100 transferred. The system maintains a state machine that applies events to compute the current balance and validate new commands. This approach gives us full traceability of every wallet state change, makes rollback logic cleaner, and helps support replayable and auditable transaction histories. In short, this high level design balances performance, consistency, and fault tolerance, making it suitable for real time digital payment systems. In this deep dive, we explore how event sourcing supports a reliable and high performance digital wallet system. We begin with the file-based command and event list. Every incoming command, such as a transfer request, and its resulting event, like balance debited or balance credited, is appended to a file-based log. This append-only model ensures immutability and auditability, making the system highly traceable and resilient to failure. If a crash occurs, we can replay these logs to reconstruct the state. To enhance performance, we cache recent commands and events in memory. This helps avoid frequent disk I/O, especially when accessing recent activity, which is common in financial applications. It improves responsiveness and throughput, while still retaining durability by eventually flushing to disk. The system maintains a file-based state, a current-derived view of account balances built by applying the logged events. This design ensures we don't rely on mutable database rows for critical state, improving determinism and reliability. To accelerate recovery and reproducibility, we use snapshots. A snapshot is an immutable, point-in-time copy of the system's state. Instead of replaying all historical events from the beginning, we load the latest snapshot and replay only the subsequent events. For example, if we have 10 million historical events and a snapshot at event number 9,500,000, we only need to replay the last 500,000 to recover the state. All these mechanisms combine into a reliable, high-performance event sourcing engine. The architecture supports strict consistency, fault tolerance, traceability, and scalability, all of which are critical for a financial-grade digital wallet. This model also naturally enables future features like audit trails, transaction replays, and eventual consistency across distributed components.